Professor Dave here. Let's talk about the Bohr model of the atom.
He knows a lot about the science stuff. Professor Dave explains.
Once Einstein extended Planck's idea of energy quantization to electromagnetic radiation, other physicists made some similar strides. Niels Bohr was dealing with some problems that were arising with the structure of the atom. If an atom has positively charged protons and negatively charged electrons, why are atoms stable? Why don't the electrons just collide with the nucleus? And what were these emission spectra that we can see? What is it about different elements that makes them emit light of different colors? Bohr answered these questions with his model of the hydrogen atom. He extended the idea of energy quantization and said that the potential energy of the electron in a hydrogen atom is also quantized. This means that an electron can't have any imaginable energy, but can only inhabit certain energy levels that are at fixed distances from the nucleus. Each type of atom has its energy levels at different values due to its unique number of protons in the nucleus. And an electron will transition from one energy level to another when a photon of a very specific energy is either absorbed or emitted by the electron. The energy of the photon will correspond to the difference between the two energy levels. So if the electron in a hydrogen atom goes from the n equals 3 to the n equals 2 energy level, a photon will be emitted that is equivalent to that specific energy gap. Another transition has a different energy gap associated with it, and therefore generates a photon of that particular energy. And to go from lower to higher energy levels, an electron must absorb a photon of that particular energy. For a hydrogen atom, the energy levels depend on the Rydberg constant and are given by the following equation. But we typically just measure the change in energy of an electron during a transition, so we can modify this equation to include the change in the energy level. N final is where the electron ends, and N initial is where it begins. Using this equation, we can predict the wavelength of photon associated with any possible transition for the hydrogen atom. Take this transition, for example, from 4 to 2. Plug in where the electron starts and where it ends, and we get the change in energy of the electron, which equals the energy of the photon. From energy, we can get frequency, and from frequency, we can get wavelength. We group the transitions according to the energy level they land on. All the ones that end on n equals 1 are called the Lyman series. The ones that end at n equals 2 are the Balmer series, and so forth. Notice that the energy level gaps decrease as n increases, and n equals infinity is actually a finite distance from the nucleus. If an electron goes beyond that, it is considered to have been ejected from the atom. The Balmer series happens to contain transitions that generate photons of visible light. These are the ones found on hydrogen's emission spectrum. These lines correspond to the electron's transitions that end at n equals 2 and the resulting photon that transition emits, which just happens to fall in the visible spectrum. As we said, these energies are unique to hydrogen. Every element will have its own emission spectrum because every element has a unique nucleus and therefore differently spaced energy levels. In this way, an element's emission spectrum is sort of like a fingerprint unique to that element. This is how we can know the composition of objects in space, by analyzing the light we see. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.